Welcome to the final lecture of week 7. In this lecture, we will quickly wrap up our discussion of infinite series. This is because all of you have taken already a calculus class in which you have seen some of this material before. In particular, we have all completed a number of homework questions on applying various series convergence tests. In this lecture, we will focus on series convergence tests not from the application point of view, but from the point of view of why do they work. As you will see, the driving force behind all of these tests we will discuss is the Cauchy criterion for convergence, of which we summarized the version for series in the last lecture. We will not be covering all of the convergence tests in full strength listed in the textbook. In today's lecture, we'll only cover the alternating series test, the comparison test, and the convergence half of the ratio test. Of the common tests that are seen, what we will omit are the divergence half of the ratio test, the root test, and the integral test. The last item because we have not and will not have time for discussing integral calculus in this course. Okay, let's get started with the convergence tests. Our first convergence test is the alternating series test. Many of you have already seen a pictorial proof of the test in your calculus textbook. We will try to make the argument rigorous. The test says, if the sequence x sub n has positive terms and monotonically decreases to 0, then the infinite series whose terms are minus 1 to the power n times x sub n converges. Notice that the series is not just adding the positive sequence x sub n. It is adding the sequence but with enforced alternating sign. But why does this test work? Or better yet, what do the assumptions give us? Intuitively, we should think of the alternating signs with the decreasing magnitudes, meaning that we are in a situation where we're traveling along a switchback and the lengths of the segments get smaller and smaller. One way to capture this is by looking at the odds and evens separately. Let us write S sub m as the partial sums of the series. Notice that by our choice of alternating, S sub 1 is negative, and S sub 2 is bigger than S sub 1, and S sub 3 is smaller than S sub 2. And so we see that the successive even terms going from the second to the fourth term, say, will be decreasing. This is because the difference between S4 and S2 is the term x4 minus x3, and x3 is larger. On the other hand, the difference between S5 and S3 is the sum x4 minus x5. With x4 larger, this means that going term to term along the odd terms of the sequence is increasing. Finally, going from an even term to the next odd term, the sequence decreases, while going from an odd term to an even term, the sequence increases. So, combining these four facts together, we can summarize by saying the odd terms of the sequence of partial sums form an increasing subsequence. The even terms of the sequence of partial sums form a decreasing subsequence. And all even terms of the sequence of partial sums are larger than any odd terms of the sequence. All of these are due to the fact that we have alternating signs and that the original sequence x sub n is decreasing monotonically. There is one property we haven't used yet of the original sequence x, that it converges to 0. This we will use on the next slide. Now, the conclusions we drew on the previous slide can be used to say the following. First, every odd partial sum is an eventual lower bound. This is because all odd terms following it is greater since the odd subsequence is increasing and all even terms are greater than any odd term. Second, every even partial sum is an eventual upper bound. This is because all even terms following it are smaller since the even subsequence is decreasing, and all odd terms are smaller than the even terms. These also show that for any capital N, if j and k are terms that happen later than n, both s sub j and s sub k sit in the interval between s sub n and s sub n plus 1. Since the distance between s sub n and s sub n plus 1 is exactly the term xn plus 1, this tells us that for every n, any two future terms of the sequence of partial sums differ by no more than xn plus 1. Since the original sequence x goes to 0, and this is where we're using that the assumption, this means that for every epsilon, there is some capital M such that all later terms are less than epsilon. Using that same M, we see that all later terms of the sequence of partial sums, not the original sequence, the sequence of partial sums is also less than epsilon. And this shows that S sub m is Cauchy, and hence the sequence of partial sums converge. And hence the alternating series converge. Again, the basic idea of the proof is very well conveyed by the zigzagging pictorial description you may have already seen in a calculus textbook. What we're trying to do in the past two slides is to show how we can formalize this intuitive picture and crystallize it into a mathematical proof using the definitions we are given. As you may have already noticed, quite a few of the things we're doing in this course concern objects that you have already learned about and methods you have already practiced in a calculus class. And you have developed many intuition about how these things work. As I mentioned in the syllabus and in the welcoming videos, a major purpose of this course is to get you to communicate mathematics effectively. This, in particular, means getting you to practice converting your intuition understanding into a sequence of mathematical arguments. So I wish you would take the time to look at the slides and try to fit each part of the proof given here against what you have intuitively know about how alternating series work. Okay, let's move on. The next theorem we'll prove in this lecture is the comparison test. And from it, we'll derive a consequence, as a consequence, the absolute convergence test. The comparison theorem says that if x is a sequence with non-negative terms whose infinite series converges, and if y is a sequence whose terms may be negative or positive, but we know that term by term the magnitude of the term yn is no more than the value of xn, then the series for y converges. Intuitively, this makes sense. Imagine the infinite series for x represents making a successive list of corrections. That the series converges means that the final state of our object after making these corrections settles down. So if we were to make less correction at every single step, which would be what the comparison means, then the series corresponding to the smaller corrections, namely y, should also converge. But why is the absolute value important? A bunch of heavy lifting for this theorem is done by the following lemma. This is a consequence of the triangle inequality for the absolute value, which shows up as lemma 29 on your usable, not 29, which shows up as a lemma on your usable statement sheet. The lemma here says, for any sequence y, its summation from k to j in magnitude is no more than the summation of magnitudes. Of course, the sum could potentially be much smaller. Imagine that yn is alternating, say minus 1, 1, minus 1, 1, and so on. Then the magnitude of any summation will be no more than 1. but the summation of magnitudes will get as large as j minus k plus 1, the number of terms being summed. So this can be a heavy overestimate, but the lemma says that this estimate is always valid even if it is too generous. I will leave the proof of this lemma to you on your exercise sheet. It is an application of induction. So with the lemma, the comparison theorem can be proven using the Cauchy criterion in a clever way. Start with some epsilon positive. There exists some n such that if j is larger than k and both are larger than n, then the sum of the sequence x between the terms k and j is less than epsilon. This is using the fact that the Cauchy criterion gives us an if and only if between this statement and the convergence of the infinite series. And we assume that the infinite series converges. Also, since the terms of x are all positive, we know that the finite sum has positive value, so we don't need the external absolute value sign. Next, we compute the analogous term for y. If I take the absolute value of the sum of the terms of y between k and j, using this lemma from the previous slide, I can say that this is no more than the sum of the corresponding absolute values. Every single one of the terms being smaller than x means that the total sum is less than the corresponding sum of x. And so, because the sum of x is less than epsilon, so is the sum of y. And so, we have found that given an epsilon, the capital N that demonstrates the Cauchy property for the series sum of x also works as the capital N that demonstrates the Cauchy property for the series sum of y. And this shows that the series of y satisfy the Cauchy property and the infinite series converges. So again, the method goes something like this. Start from the convergence of the series of x. Use the theorem from the last lecture to say that this is equivalent to the partial sums of x having the Cauchy property. We convert this into saying that the partial sums of y have the Cauchy property, and hence using the theorem from last lecture again, we get that the infinite series for y converges. So the goal of this proof is demonstrating the middle step, how to convert the Cauchy property for x to the Cauchy property for y. And this, we use the lemma that is a generalization of the triangle inequality for absolute values, and the assumption that term by term the absolute value of y is less than x. So that's the proof. One quick application of the comparison test, stated in this way, is the statement that if a series is absolutely convergent, then it is convergent. It is a simple substitution from the previous theorem. The series that was called x in the comparison theorem is the series of absolute value of x here. The series that was called y in the comparison theorem is the series x here. And so by definition, the absolute value of x is no more than the absolute value of x, which in the terminology for the previous theorem is a statement that absolute value of y is less than x. And hence, absolute convergence implies convergence. And now we arrive at the final theorem on series that we will discuss. This is the ratio test. Now, if you remember the test from Calculus 2, you will remember that the ratio test you saw there says if the limit of the ratio is less than 1, then the series converges. If the limit is greater than 1, then the series diverges. If the limit is equal to 1, then the test is inconclusive. We will only study the convergent case in this lecture, mainly to demonstrate the principle. The theorem we will prove here says that if x is a sequence with non-zero terms, such that the lim sup of the absolute value of the ratio of the next term over the previous term is less than 1, then the series converges. The assumption of having non-zero terms is just to avoid the possibility of dividing by zero, and does not have a huge significance in the proceedings. The key assumption here is slightly more relaxed than what you saw in calculus. In the calculus class, we require the limit of the ratios to converge. Now in analysis, we just require the lim sup of the ratios to be less than 1. Remember, any eventually bounded sequence has a lim sup, so this is a much less restrictive assumption than requiring the limit to converge. Before going on to show you the proof, I want to mention in passing that the divergence statement for the ratio test would say that if the lim inf of the sequence of ratios is bigger than 1, then the series diverges. So what is the idea behind the proof? The idea is essentially that if there is a limiting ratio from one term to the next, then our series is approximately a geometric series. And we know that geometric series with ratio less than 1 converges. So our goal with the proof is to try to compare our series to a geometric series. To implement this comparison, we first do some reductions. First, we may assume that each of the terms of x sub n is positive. Notice that since in the crucial condition of the lim sup of the ratios, we took an absolute value, this means that the lim sup computed doesn't depend on whether x sub n is positive or not. So we can just replace each term by its absolute value. This step also means that in fact, the conclusion of the theorem should be that the series converges absolutely. In any case, moving on, using the Archimedean property, if the lim sup of the ratio is strictly less than 1, then there is a number r between the lim sup and 1. And since r is bigger than the lim sup, we see that r is an eventual upper bound. This means that there exists some capital N such that for all later terms, the ratio x sub n plus 1 over x sub n cannot be greater than r. We can apply this to compute the ratio of terms that are not just one term apart. The ratio of x sub n plus m over x sub n can be written as the products of x sub n plus m over x sub n plus m minus 1, and so on until the ratio of x sub n plus 1 over x sub n. Notice that in this string, the denominator of one term cancels the numerator of the next, and so the string indeed reduces to x sub n plus m over x sub n. Now, each of the ratios, provided that small n is at least capital N, is less than r, since r is an eventual upper bound of the ratios. So we can say that x sub n plus m over x sub n is no more than r to the power m. We summarize this computation by saying that for every j bigger than n, we have x sub j is no more than x sub n times r to the power j minus n. And now we see we are already most of the way to what we want. This comparison pretty much says that after the nth term, the terms of x are smaller than that of a geometric series, and so we have convergence by comparison. Let's make this precise. We will use the Cauchy criterion again rather than the comparison theorem. This is because the comparison theorem, as we stated it, will require that every term of x is less than a geometric series. We don't know if that is true. We only know that this happens eventually. Now, it is in fact true that we can have a version of the comparison theorem that only requires comparison to hold for all sufficiently large indices. I encourage you to think about how to prove such a comparison theorem by modifying the previous proof. And with such a theorem, you can then prove the ratio test using the comparison established in the previous slide. But let's proceed by working with our hands dirty using the Cauchy property. So we should start with j and k bigger than n. Then the sum of x from k to j can be controlled like this. Using the geometric series like comparison from the last slide, we replace each term in the sum by x sub capital N times a power of r. Doing some algebraic manipulation gets us to the term after the first inequality. What we did here is pulled out the common factors, so we have left over a geometric sum. Using what we talked about in lecture 3 about geometric series, this sum can be evaluated. The evaluation yields a fraction whose numerator is 1 minus a power of r. Since r is less than 1, so is any of its power. So 1 minus power of r is no more than 1. So we just drop the numerator and end up with the final expression. The advantage here is that this expression is some fixed number times r to the power k, where the fixed number is x sub capital N times r to the minus n power divided by 1 minus r, and is entirely independent of k. So we can apply the Archimedean property of lemma 29 to make r to the power k as small as we need. Since j and k are arbitrary, if they are both bigger than some large k, then this guarantees that the sum from j to k is less than some epsilon. And this shows that the series has the Cauchy property and hence converges. And this ends the proof. It may be a good idea to take a few minutes to make sure you understand all the algebra that is involved here, specifically all the steps that were not shown on the screen. Let's just give a quick recap of what we did in this lecture. The first theorem we proved is the alternating series test. The idea is that we wish to regard a series as describing successive corrections or nudges, with each later nudge with a smaller magnitude but in an opposite direction. This we discover shows that the sum total of all future corrections past the point capital N are going to have effect no larger than the effect made by the corrections at step N. So the fact that the magnitudes of the corrections goes down to 0 means that the sequence of partial sums converge. The second theorem we proved is the comparison test. What we did there is to pass the Cauchy property of a positive series to obtain the Cauchy property of a series whose terms in magnitude are less than the convergent original series. And the third theorem here is the ratio test, where we essentially try to compare the series satisfying the hypothesis of the ratio test against a geometric series. And using the experience we developed from thinking about geometric series, we're able to prove that the Cauchy property holds for the series we are interested in. As you can see, the common theme behind all these arguments in various different levels of technical difficulty is that we proceed by trying to transfer the convergence from something we know about to the convergence of something we are studying. And that one of the most convenient ways of doing so is by using the Cauchy criterion for convergence, be it the version for sequences or its implication for series. This is the general method behind all series convergence tests. So, this ends week 7. Just to recall, this week we started by doing some touching up on our understanding of the lim sup and lim inf operations, and then ended with a whirlwind tour of infinite series. This ends our module on sequences and their limits. Starting next time, we'll try to apply some similar ideas to study properties of functions on the real line, specific their continuity and differentiability. See you next week.